Section 2, we will continue to look at properties of exponents as well as scientific notation. First, let's use the quotient rule to simplify x to the fourth over x to the sixth. In the last section, I mentioned that there was a shortcut for simplifying when we use the quotient rule, and this is where I will explain that. Typically, we would take our x and write it one time, write the exponent from the top, and then subtract the exponent from the denominator. This will give us x to the negative 2. And on the next slide, we'll look at how to handle dealing with negative exponents. But instead of going through the process of simplifying and then adding an additional step to simplify a negative exponent, this is the process I go through instead. First, we look at the identical bases, which in this case is x, and we compare the exponents. We can see that 6, which is the exponent of the denominator, is greater than 4, the exponent for the numerator. Wherever we have the greatest exponent, that's where all of our exponents will go. So I'm going to write the base one time in the denominator. We take the larger exponent minus the smaller exponent, or in this case, 6 minus 4, which will leave us with an exponent of 2. Now, because all of our x's gravitated toward the denominator, we have to put a placeholder in the numerator, which will be a 1. So this would equal 1 over x squared, which is identical to x to the negative 2. But in order to be simplified, we want to eliminate any negative exponents we see. This is the last property of exponents that we haven't seen so far, which is the property of negative exponents. And this fits exactly the last example we saw, where we had x to the negative 2 equals 1 over x to the positive 2. Another way to say this, if we had a negative exponent in the denominator, let's rewrite this as 1 over a to the negative n. That would be the same thing as a positive exponent in the numerator. And so this rule can be used either way, taking a negative exponent from the numerator and moving it to the denominator, or a negative exponent from the denominator and moving it to the numerator. Let's try to do that with the next few examples. We want to simplify by writing each result using positive exponents only. So using the negative exponent property from the last page, 3 to the negative 2 can be rewritten as 1 over 3 to the positive 2. Now at this point, any numbers raised to a power we want to simplify. So this would be 1 over 3 squared is 9, or 1 over 9. Example, we have x to the negative 7, which can be rewritten as 1 over x to the positive 7. At this point, we have no numbers that need to be simplified, so we would be finished. And the last example, 2x to the negative 4. It's important to note that the negative 4 only applies to the x. It would never apply to the 2 unless the 2x was in parentheses. So in this example, the 2 will stay in the numerator. It doesn't need to move to the denominator because it does not have a negative exponent. So 2 stays in the numerator, x will move to the denominator, and we'll now have a positive 4 as the exponent. Do the same thing with the next 3 examples. First, we have negative x to the negative 3. Again, remember the negative 3 only applies to the x. It would apply to the negative if the negative and the x were in parentheses together, but here they are not. So we'd rewrite this with the negative, which really represents negative 1 remaining in the numerator, and x cubed in the denominator. Remember, the sign of the exponent changes. The sign of the entire term will not change. So this remains a negative fraction, even though we changed the sign of the exponent. Let's try the same thing with part B. We have negative 3 raised to the negative 2. And just like in example A, the negative 2 only applies to the 3. It does not apply to the negative because we do not have parentheses that trap the negative with the 3. So we rewrite this as negative 1 because the negative stays in the numerator over 3 to the positive 2. 3 to the positive 2 is 9, so this becomes negative 1 over 9. The last example on this page, negative 3 to the negative 2, and in this example, negative 3 is contained in parentheses. So that is the base that the exponent is being applied to. So for that reason, we will write this as 1 over negative 3, still in parentheses, raised to the positive 2. As we simplify, negative 3 times negative 3 is a positive 9. So 1 over negative 3 squared would be 1 over 9. Make sure to be careful when dealing with negatives that are being taken to an exponent. If they are in parentheses, it will be carried along every time. If they are not in parentheses, we write it just once, and the exponent has no effect. Exponents in each of these examples, we want to rewrite these expressions with positive exponents. So for part A, we have 1 over x to the negative 3, and using the second part of that negative exponent rule, anytime we have a negative exponent in the denominator, we will take that term and move it to the numerator. So this will become x cubed. And we could write 1x cubed, but remember, 1 is a coefficient that can be invisible. So x cubed would be the simplified solution. In the next example, we have 2 negative exponents. We have x to the negative 2 over y to the negative 4. So at the same time, let's move both of these negative exponents from the numerator to the denominator, or the denominator to the numerator. So x to the negative 2 will go down to the denominator, and that exponent will become positive. Y to the negative 4, that term will move to the numerator, and the exponent will also become positive. So as we rewrite this, we still have the fraction bar, but the new numerator will be y to the 4th. The new denominator will be x to the positive 2nd power. Time on this slide, this is a summary of all exponent rules that we've shown over the past 2 sections. I will add one rule, which is an extension of the power of a quotient rule and the negative exponent rule that might be helpful in a few situations. And that is, if we have a fraction, a over c, and that entire fraction is being written as raised to the negative exponent, we could flip the fraction. We wouldn't change any of the exponents, but we would flip the fraction, and then the exponent on the outside would become positive. Sometimes this is a helpful rule as well. It's really just a combination of other rules, and that's probably why it's not written on this slide, but you might want to write it in your notes as well. By writing the following expression with positive exponents only. Now, anytime we have an algebraic fraction raised to a power, we want to start by simplifying the inside first. So to simplify the inside, the first thing I would do is change any negative exponent to a positive exponent. And we're going to do it like this. I'm going to circle my negative, or my terms with my negative exponents, and draw arrows indicating they will move to the denominator or to the numerator. So 3 to the negative 2 needs to move down to the denominator. In the denominator, we have 3 to the negative 4, which needs to move up to the numerator. We also have b to the negative 3, which needs to move up to the numerator. So that would be the first step. We rewrite this. We now have a 3 to the 4th power in the numerator. We still have a cubed. We still have b. And we also have b cubed. So we have 2 additions, and you can see that 3 to the negative 2 is no longer in the numerator. In the denominator, we have 3 to the positive 2, as well as a to the 7th. And this is all still being raised to the negative 2. At this point, we're going to use the quotient rule and the product rule, depending on the placement of the terms and the variables. Because the 3's are stacked up in division, we're going to write that 3 one time. We're going to subtract the exponents. We just have to decide if we're going to subtract the top minus bottom or bottom minus top. As we compare those two exponents, the 4 is greater than the 2, and because the 4 is the exponent in the numerator, our 3's will all move to the numerator. So write 3 in the numerator, we subtract largest exponent minus smallest exponent, and that becomes 3 to the second power. 4 minus 2 is 2. We now look at the next terms, which are the a's, or the next factors, which are a's, and the a's are also stacked up in division. So we compare those exponents. We have a 3 in the numerator, a 7 in the denominator. Because 7 is greater than 3, all of the a factors, all the a terms will move to the denominator. Again, we take the largest exponent minus the smallest exponent. 7 minus 3 is 4. So we're left with a to the 4th in the denominator. Our b's are not stacked up in division. They're actually being multiplied. We have b to the first. Remember, it's to the first power if it's not written. B to the first times b to the third. And in this case, we add the exponents. When we multiply the bases, we add the exponents. So that will become b to the 4th power. And this entire fraction is still being raised to the negative 2. We can simplify one more time within parentheses before we deal with that exponent on the outside. 3 squared is 9, so this becomes 9 b to the 4th over a to the 4th, all raised to the negative 2. Now let's use the additional exponent property that I wrote on the last slide, which stated that if we have a fraction raised to a negative exponent, we can flip the fraction to write a to the 4th over 9b to the 4th. We don't change any signs on the inside. We can flip the fraction and change the sign of the outside exponent. Now we use the power of the quotient rule, and we rewrite this as a to the 4th all to the second power over 9 to the second power b to the 4th to the second power. Any place where we have multiple exponents, such as a to the 4th to the second power, we multiply, so that becomes a to the 8th over 9 squared is 81, b to the 4th raised to the second power, we multiply exponents again, that becomes b to the 8th. Now there are other ways to work this problem in terms of what rule you use first, how you decide to go about the problem. I think this is the most straightforward way by simplifying inside parentheses. If you find that another way works better and you do other steps in a different order, that's fine, as long as you end up with the same result. Let's now switch gears and talk about scientific notation. And the reason we lump scientific notation in with exponent properties is because we use 10 raised to different powers. And since we have 10 raised to different powers when dealing with scientific notation, sometimes we need to use different exponent properties in order to find a result. In many fields of science, we encounter very large or very small numbers, and scientific notation is a very convenient shorthand for expressing these types of numbers. So we know we have a number written in scientific notation if it is a positive number written as the product of a number, which we'll just denote with a, where a is between 1 and 10, and this is very important. A has to be between 1 and 10. And that a is being multiplied by an integer power r of 10. So we will have a times 10 to some power, and that power could be a negative or a positive number. These are the steps we will use to write a number in scientific notation. Step 1, we move the decimal point in the original number so that the new number has a value between 1 and 10. Sometimes we'll move the decimal to the right, sometimes to the left, but we move the decimal so that our new value is between 1 and 10. Step 2, we count the number of decimal places that the decimal point is moved in step 1. If the original number is 10 or greater, so we have a number larger than 10, then we say that we have a positive exponent. If the original number was less than 1, then we would have a negative exponent. And the last step, we multiply the new number that we found in step 1 by 10 raised to the power we found in step 2. Let's try to write each of the following numbers in scientific notation. So we start with 4,700. Let me write the decimal point so we know where it is. It always is at the end of the number on the right side if it's unwritten. So we move the decimal point as many times as is necessary until we have a new number that is between 1 and 10. So we will have to move to the left 1, 2, 3, and we now have 4.7. So when I move the decimal 3 times, we have 4.7. And that 4.7 will be times 10. We need to decide if it's going to be a positive 3 or a negative 3. Think of it this way. Many people would say that if they stepped on the scale and they saw a large number, and later after diet, exercise, sickness, whatever, they stepped on the scale and saw a small number, that would be a good thing. That would be something positive. So if we take a number larger than 10 and we shrink it, we make it smaller, that is a positive number. So here this would be a plus 3. And our scientific notation will be 4.7 times 10 to the positive 3, or 10 to the third power. Let's try the next example. We have 0.00047. Again, here we have the decimal place written, so we don't have to write it in. But we need to move the decimal so that our number is between 1 and 10. So starting at the decimal, we move to the right 1, 2, 3, 4 times. So in this example, we also have 4.7 times 10, and we need to decide if that 4 is going to be a positive exponent or a negative exponent. If we start with a really small number and we make it larger, we would say that is a negative value. So negative 4 will be our exponent. In general, to write a scientific notation number in standard form, so now we want to go the opposite direction, we would move the decimal point the same number of spaces as the exponent on 10. If the exponent is positive, move the decimal point to the right. If the exponent is negative, move the decimal point to the left. So we would use the same standard notation, negatives being to the left, positives being to the right. Let's try to write the following example in standard notation. So the exponent tells us how many times we will move the decimal, and in this case it's 3. We find the decimal, and because it's positive numbers are to the right, we move the decimal to the right 3 times. 1, 2, 3. Now the decimal is between 3 and 8, and our number in standard notation will be 5,273.8. We can also perform different arithmetic operations with scientific notation. The two we will look at are multiplying and dividing. And when we multiply and divide numbers in scientific notation, we will use properties of exponents. So to begin, let's look at 7.3 times 10 to the negative 2, all multiplied by 8.1 times 10 to the 5th. When we multiply numbers in scientific notation, we first multiply the whole numbers that are not 10. That's not 10 raised to the power. So we multiply 7.3 and 8.1, and that gives us 59.13. Once we multiply the whole numbers, we will then add the exponents on 10. Remember, the property of exponents, if we were multiplying the same base, we added the exponents. So this becomes 59.13 times 10 to the third power. Negative 2 plus 5 is 3. Now at this point, we want to rewrite our number in scientific notation as a number in standard notation. The 3 tells us we will move the decimal place 3 times to the right. Let's rewrite the number so we have enough room to do that. 1, 2, 3. So we have a placeholder of 0. And our number in standard form is 59,130. Similarly, let's divide two numbers in scientific notation. We start with 1.2 times 10 to the 4th. all divided by 4 times 10 to the 9th. So the numbers that are not 10 raised to a power, we will start by dividing those. 1.2 divided by 4 is 0.3 times. Now with the exponents of 10, we will subtract. And regardless of where the larger and smaller exponents are, we will subtract top minus bottom. So this will become 10 to the negative 5. If we want to rewrite this in standard notation, we first look at the exponent. Because it's negative 5, we move our decimal 5 times to the left. So we rewrite 0.3 and allow ourselves enough room to do that. Now we move the decimal 5 times to the left. 1, 2, 3, 4, 5. We fill in all of our gaps with zeros. And so the number, the answer in standard form, we have 5 zeros and a 3 all behind the decimal.